In this video, we will be learning about applications of right triangles. The three kind of pieces of information that we're going to be using all together are Pythagorean's theorem, the fact that all of the angles in a triangle add up to 180 degrees, and our SOHCAHTOA ratios. One thing I will point out before we get started is the setup for all of these triangles is that our capital letters will represent our angles, and our lowercase letters will represent the side opposite that angle. So for example, here's the angle capital A. Opposite that is the side lowercase a. We will always use capital C to represent the 90-degree angle and lowercase c to represent the hypotenuse, the side that is opposite that. So starting with example 1, we want to solve this right triangle. Solving the triangle means finding all of the missing values that we were not given. So in this problem, we were not given capital B, and we were not given lowercase b, and we were not given lowercase a. Note that we do know that capital C is definitely 90 degrees. So I'm going to start off and look for capital B. That'll be the easiest thing for us to find because we know the other two angles in the triangle. We can find it by taking 180 and subtracting the other two angles that we have in the triangle, the 28 degrees and the 90-degree angle, to get the capital B is 62 degrees. The next thing I'm going to look for is lowercase a. So lowercase a right here, relative to the 28 degrees that we have, that is opposite of it, and we also have the hypotenuse. So we could use sine equal to opposite over hypotenuse. Opposite is a, hypotenuse is 14.8. I'll take both sides of that equation and multiply it by 14.8 to get rid of the fraction, to see that little a is equal to 14.8 times sine of 28 degrees, which gives us that little a rounded to one decimal place is approximately 6.9. Next, I'm going to find little b. This time to find little b, I'm going to work with the capital B angle, which we said earlier was 62 degrees. You could have still worked with the 28, it's just that you would have had to use cosine, because little b is adjacent to 28. So using sine again, because from 62 degrees, the opposite side is b, and the hypotenuse side is still 14.8. Similarly, we're going to multiply both sides of this equation by 14.8 to get rid of that fraction, to get that b is equal to 14.8 sine 62, which is approximately 13.1. And so that solves our triangle by finding all of those missing values. In example 2, we start off and we do not know lowercase b, so we're missing one side and we're also missing capital A and capital B. So to find the side that we're missing, I'm going to get started with Pythagorean's theorem that tells us that a squared plus b squared is c squared. We're going to plug in what we already know, and then actually just go through evaluating this. 20 squared gives us 400. We need to subtract 81 from both sides to see that b squared is equal to 319. And then we'll take the square root to get that b is equal to the square root of 319. I will approximate that to one decimal place to give me approximately 17.9. So we have an answer for b. Now we have an answer for lowercase b. To find the two missing angles, we're going to need to use some inverse trig. Because, for example, relative to the capital A, we were given the opposite side and the hypotenuse. So we know that sine of capital A is 9 over 20. That's just opposite over hypotenuse. And so I know that capital A is equal to sine inverse of 9 over 20. And I'm going to round that to just one decimal place, and that gives me approximately 26.7 degrees. Now, when you're using an inverse trig to find a missing angle, make sure that you're using exact values for sides and not approximations. So what I mean by that is, say we're looking for capital A, and we can say, oh, well, we have the adjacent side, and we have the hypotenuse, because we did work to find the adjacent side of B already. What you would not want to do is say that cosine A is adjacent 17.9 over hypotenuse, because this answer has already been rounded. We don't want to use rounded answers to find more answers that we're going to round. So if anything, if you were going to use cosine there, make sure that you would go back and put in the exact value of what the adjacent side is, the square root of 319 before we approximated it, but do not use an approximation to find another answer. That's how you end up with rounding errors. Okay, so the last angle we have to find is capital B. We will take the fact that all of the angles in the triangle add up to 180 degrees and subtract the two angles that we had already found to find that capital B is equal to 63.3 degrees. And that solves our triangle by finding all of our missing values. In example 3, we have our first word problem where we have that a surveyor standing on level ground 100 feet away from the base of a lighthouse. So I know that the base of this is 100. He measures the angle of elevation to the top of the lighthouse. So that is measuring there to be 18 degrees. And we are asked to find to the nearest foot how tall the lighthouse is. So relative to the 18 degrees, what we're looking for is the opposite side. And what we have is the adjacent side. So we're going to use tangent because we know that tangent of 18 degrees is opposite side of x over the adjacent side of 100. To solve this equation for x, we need to multiply both sides by 100 to see that x is 100 tan 18 degrees. And then I will approximate this to the nearest foot to get 32 feet. Example 4 is very similar, but a little bit different, because this time we have the surveyor standing on the ground again, but he is 90 feet from the base of the lighthouse, and they tell us that the angle that's measured from eye level to the top of the lighthouse is 28 degrees. So from his eye level to the top of the lighthouse, we have a 28 degree angle measured there. They go on to tell us that his eye is 5 feet above the ground. So this vertical distance here is 5 feet above the ground. And they're asking us for what is the height of the lighthouse. So we're going to be able to use this triangle here that I'm outlining in green to figure out what this distance is there, that vertical distance, I'll call x. And then once we have that, we're going to have to remember to add back in the 5 feet from the bottom to get the total height of the lighthouse. So let's work in just solving that triangle first. So in this triangle, that looks weird. In this triangle, we have a 28 degree angle, and we know that this is 90 feet away, and we're looking for that side opposite the 28 degrees so we can get some of the height of that lighthouse. We're going to be using the tangent function again because we want the opposite and we have the adjacent. So tan 28 is opposite over adjacent, that's x over 90. To solve that equation, we will have to multiply both sides of the equation by 90 degrees to get rid of that fraction. So that gives us that x is equal to 90 tan 28, which is approximately 48 feet. So to get the total height for the lighthouse, we're going to take that 48 feet and add it to the 5 feet that we had at the bottom. So we just found that was 48. We add that to the 5 at the bottom to get a total height of the lighthouse of 53 feet. In example 5, we have that two different measurements are being taken from the ground that is 90 feet from the base of the lighthouse here. One measurement is going to the bottom of the window, and another measurement is going to the top of the window. Okay, so the measurement that's going from the bottom of the window, they tell us is 36 degrees, and the measurement going to the top of the window is 42 degrees. We're being asked to find the height of the window. So how we're going to do this is we're going to think of this as two separate triangles. One where we can find this vertical distance to the bottom of the window, that I will call x, and another where we can find this vertical distance to the top of the window, which I will call y. So we'll have to find y and find x and then subtract them. So we're really working with two separate triangles here. We're working with the smaller triangle that has the 36 degree angle, and the side opposite that is x. it still has a base of 90. And we're also working with the larger triangle that has the 42 degree angle. The opposite side is y, and it still has a base of 90, not a degree. So we're going to have to go find x and y. So starting with the first triangle, to find x, we're looking for the opposite side of our 36 degrees, and we have the adjacent. So we're again going to use tangent is equal to opposite over adjacent. In order to solve for x, we will need to multiply both sides of this equation by 90. And then I'll approximate 90 tan 36 in my calculator to get about 65.38. For the second triangle, to find y, very similar setup. We're still going to use tangent. This time we have a 40 degree angle. Opposite over adjacent, that's y over 90. We will need to multiply both sides by 90 in order to get y by itself. And 90 tan 42 is approximately 81.04. So now that we have both y and x, we can find the height of the window by subtracting them. So we're going to take this 81, I'm going to go ahead and start rounding here because we're rounding to the nearest foot. So this 81 minus 65, taking the 81.04, subtracting the 65.38, and that gives us that the window is about 16 feet tall. There's a follow-up question after example 5 that asks from the given information if we're able to figure out the total height of the lighthouse. And the answer is no, because we don't have any information about what's going on with the top piece of the lighthouse, the piece that's on top of the window. So had there been another measurement taken in here that would have given us that angle, then we would have been able to finagle and figure out how much is left on top. But because we don't have that information, no, we cannot find the total height of the lighthouse. In example 6, we have an observer who is hovering 200 feet above sea level, and they're making measurements to two different points in the ocean, point A and point B, and we're given the two angles of depression to those 2 points respectively. Now it's important to remember that when you're sketching an angle of depression, you need a horizontal from your observer. Our observer is in the helicopter, so we need this horizontal here from the observer before we can sketch in those angles of depression. And we're told that the angles of depression are 44 degrees, so this is a 44 degree angle, and 35 degrees, respectively. We want to find how far apart those 2 points are in the ocean. So we're going to think of this as two separate triangles. One triangle over here on the left, with this distance I will call x, and a separate triangle over here on the right, with this distance that I will call y, and we will have to find x and y and then add them together. Now inside these triangles, we need to actually get some angles on the inside of them, which we use those angles of depression to do. So rules of geometry, or if you think about right triangles and how this is a right angle, then that tells us that that angle up there must have been 46. And so we can calculate that this angle down here is also 44 degrees. So if you think back to parallels and transversals, if this is 35 degrees, this alternate interior angle must also be 35 degrees. So now that we have some angles on the inside of the triangle, we can start doing some right triangle trick. So inside of the first triangle, I'm trying to find x. That is adjacent to the 44 degrees. And we have the side that is opposite, the 200. So we would again be using tangent. The fact that tangent of 44 degrees is opposite over adjacent. That's 200 over x. We need to solve that equation for x. So first thing I'm going to do is just get rid of the fraction by multiplying both sides by x. And then to finish solving for x, I'm going to divide both sides of this equation by the tan 44 degrees. So we get that x is equal to 200 divided by tangent 44, which is approximately 207 feet. And now we'll do a very similar thing on the other side, but this time we're using the 35 degree angle. The side opposite that in the triangle is 200. The side we're looking for adjacent to that is y. we're again going to get rid of the fraction in this equation to start off. Remember, we're trying to solve for y so that we can add it to x. And so to get y by itself, we will need to divide both sides of this equation by tan 35. And 200 divided by tangent 35 is approximately 286. So now that we know x and y, we're able to add them together. So 207 plus 286 gives us an approximate distance of 493 feet between those 2 points in the ocean. Now, before we move on and look at different types of word problems, we need to make sure we understand what a bearing of an object is. So bearing is used to measure angular relationships between 2 points, and I'll explain with this example. So we have a point A and we have a point B. The first thing we have to do is put a north-south axis running through our first point, the point that we are measuring the bearing from. So this is a bearing measured from A to B. So once we have that north-south axis in, we have to make a choice. Either we're going to come off the north axis and go towards the ray where B is at, or we're going to come off the south axis. So you either come off the north or you come off the south to measure a bearing. How you choose is whatever angle you get when you go to that ray has to be acute. So when I look at the angle from when we came off the north in orange, that is not an acute angle. So we would not use that because that angle is bigger than 90 degrees. The angle in blue at the bottom, which is labeled in 40 degrees, that is an acute angle. And so that's the one that we would use. So that tells us that we definitely came off south and we are heading towards the west. So we came off south and we're heading towards the west. How far did we head towards the west off south? Well, we went 40 degrees. So that is a south 40 degree west angle. So your setup for bearings is always going to be either north or south first, and then some angle, and then it's either going to be east or it's going to be west. So it could be north something west, or it could be south something east. But this first component here is always north or south, and your second component is always east or west. And it depends on how far in that direction you went. So let's look at some examples where we measure some bearings. So looking at this picture, we're definitely going to have to be coming off of the north axis to get to that bearing, to get to that ray, because if we come off the south axis, that green angle is not acute. So how far off the north axis did we come? Well, we can see that they already gave us that 40 degrees there. So this blue angle here must be 90 minus 40, since this is all contained in the same quadrant, to give us 50 degrees. So we came off the north axis and traveled 50 degrees towards the east axis. So this is a north 50 east bearing. In example 8, first let's decide if we're going to be coming off north or if we're going to be coming off south. So if we come off north, that's what our angle would look like. And if we come off south, that's what our angle would look like. The angle in blue is not acute. So this is definitely going to be a bearing coming off north and heading towards west. All we have to do now is figure out how much degrees did this actually travel. Well, this orange degree measure here, we knew the entire thing was 124, but we don't want the 90 degrees that it traveled to get through the first quadrant. So I'm just going to do 124 degrees, 124 degrees minus 90 degrees to give us 34 degrees. So this is a north 34 degree west bearing. In example 9, we're going to need to come off of the south axis to get to that point B on that ray, because if we come off the north axis, that is not an acute angle. So we definitely know that we're coming off of south, heading some amount of degree that we're going to talk about towards west, so from south to west. So to figure out what that degree is, well, we know that if we had gone all the way around, that would have been down at 270. But I want to take off the 220 that it has already traveled. So this space here is 270 minus 220 to give us that this is a south 50 degree west bearing. In example 10, First, we have to make up our mind. Are we coming off of north or are we coming off of south? We're going to have to come off of south in order for this to be an acute angle, and we're heading towards the east. So this is a south, some angle, east bearing, because this is going from south to east. We know that that little space in this upper corner right here is 19 degrees, and so what must be left in that quadrant is 90 minus 19 degrees, which gives us 71 degrees. So this is a south 71 degree east bearing. In example 11, the problem is not set up originally for us to be successful because we're measuring the bearing from A, and that means that the north-south axis has to run through A. So you'll notice in all of these problems where we were measuring bearings from A, it was already set up where that vertical axis was going through A. So the hint here is to redo the problem and to make it so that there is a vertical axis running through A. So I'm going to add that vertical axis in there. I'll also add a horizontal axis in here just to help us get some perspective. I will label this. We're still looking for the bearing from A to B. So I want to know what is this bearing here. We will have to come off south in order for that to be an acute angle, because if we had come off north to get to that ray, that is larger than 90 degrees. So just from that orientation, I can automatically tell this is going to be a south something degree west. Well, looking at this picture, here we have a right triangle. We know that angle is 30 degrees. This is a 90 degree angle. So it must be that this orange space here is 90 minus 30 to give us a 60 degree angle. Because remember, we know that all angles in a triangle add up to 180 degrees. In example 12, we have that a boat leaves a marina. So I'm going to go ahead and start setting up a picture for this. A boat leaves a marina. Let's say the marina is right there and it sails north for 30 minutes. So it went north for 30 minutes. And then it sailed west for 2 hours. They tell us that the boat's average speed is 12 miles per hour, and they're asking us to find the bearing for the return trip. So on the return trip, the boat would then be starting right here. So to calculate that bearing, we would need to be thinking about a north-south axis in there. We already have a horizontal line here, and we're going back that way. So that's definitely going to be a southeast bearing. You want to know what that angle is right there for the bearing for the return trip. So keep in mind, when this says for the return trip, that definitely means you need to be starting at where the boat would start on the return trip, which would be wherever it traveled to. Okay, but the problem is that we don't have any sides on the triangle. We have times for how long it went that way, and we also have how fast it was traveling, or rather its average speed. And so we have to use the formula that distance is equal to speed times time to calculate what these distances are. So for instance, for how far the boat went north, well, they told us that the speed was 12 miles per hour, and it traveled that fast for 30 minutes, which is half an hour. So if you're going 12 miles an hour for half an hour, then you have gone 6 miles. So I will erase this 30 minutes and just label that north distance with a 6. And for as far as the boat went west, it still has the average speed of 12 miles an hour, but it traveled west for 2 hours. And so if you're going 12 miles an hour for 2 hours, then you went 24 miles. So I'm going to erase this 2 hours and replace this with 24 miles. So now that we have some sides on the triangle, we're able to use some inverse trig to figure out some angles. So keep in mind, we want to know what this green angle is right there. Well, if we knew what this angle was on the inside of the triangle, then we could find the green angle because those two angles are complementary. They form a 90-degree angle. So what I'm going to do is I'm going to use right triangle trig to figure out what that angle theta is. So relative to that theta, we have the opposite side of 6 and the adjacent side of 24. So SOHCAHTOA tells us that tan theta is opposite over adjacent, 6 over 24. We would use tangent inverse to cancel out the tangent to get that theta is tan inverse of 6 over 24, which is approximately 14 degrees. Well, if that is a 14-degree angle, then the bearing that we are looking for must be 90 degrees minus 14 degrees, which is 76 degrees. So now we know that this was a south, because we came off south, we went 76 degrees towards the east to get that bearing. And now in our final example, we have that a plane leaves an airport at a bearing of north 38 degrees west. So I'm going to go ahead and start drawing that. A bearing of north 38 degrees west means the plane went 38 degrees off of the north axis, so it's going that way. So it left the airport, the origin from where it started, had a 38 degree coming off north towards west bearing, and it's traveling 280 miles per hour for 2 hours. We're again going to have to use the fact that distance is equal to speed times time. So if you're traveling 280 miles an hour for 2 hours, then your distance is 280 times 2, which gives us a distance of 560 miles. So we know that this length right here is 560. They then tell us that the plane travels, or rather that the plane turns at a 90-degree angle to the left. So it made a 90-degree angle to the left, and it traveled an additional 500 miles. So I know that side of the triangle is 500. We're being asked to find the bearing required to locate the plane from the airport. So here is where the plane ends up. I'm going to come in and end that right triangle there. Pay attention to the fact that the bearing is being measured from the airport, which is good in our case because we already have the airport running through that north-south axis. And so what we're looking for is this angle here, the angle from that north-south axis to get to the ray on which the plane is on. So we already have part of that, as we can see here, just going up to here was 38 degrees. So if we knew what this angle was, how much further this went inside the triangle, then we could add that to our 38 degrees and be done. So to find that angle in blue on the inside of the triangle, we're going to use some more inverse trig. So relative to that angle, we have the opposite side of 500 and the adjacent side of 560. So we would use tangent, because tangent is opposite over adjacent. To get theta out of tangent, we're going to have to use tan inverse. So tan inverse of 500 over 560 gives us approximately 42 degrees. So now that we know that theta is 42 degrees, we're going to have to take the 38 degrees that we already had and add it to the 42 degrees that we just calculated to get 80 degrees. So we can see this is coming off north and traveling 80 degrees to the west to get that bearing.